Hello, everyone. My name is Joseph Kozak. I'm one of the members of the Surface Power focus group, and I get to introduce our next set of short talks, so only 10 minutes. Very excited to have you. We will give about, for the presenters, I'll give you about an 8-minute warning, and then, of course, at the 10-minute mark so that we can keep us moving along today. So first up, I do have your slides if necessary. However, I will ask you guys to take control yourselves so that you have the power and control. It's a little bit easier than with just 5 minutes. So first up, we have Mark Moensen, from Westinghouse. So Mark, please take it away.
All right, I'm getting to share my screen here. You see my screen?
See it and hear you. Perfect. Thank you.
All right, you're welcome. So thank you for having me here today. Joe talked a little bit earlier about eVinci. I'm here to talk more specifically about eVinci reliability. I'm a consulting engineer in the Nuclear Island Mechanical and Piping Systems organization in our global engineering services, and I support eVinci with technical integration, consultation, including reliability. So I won't belabor this. Joe already went over all this, so I'll skip on to the next one. So the overall problems or challenges that are unique to a microreactor of the eVinci design is that it's way different than a commercial nuclear power plant. And it operates even different than other space power plants that have been used previously by NASA. So we have very high power production availability design goals to meet the demands of our customers having remote applications for a lot of the types of things we're looking at. Remote, not as remote as the moon, but still remote when it comes to looking at this as being the sole source of power for communities and industries in certain areas for the targeted market. And we have a design goal of no maintenance for the reactor components over a pretty long refueling cycle of 8+ years. We want to have longevity of high reliability components to make sure that when we actually do cool down and swap out and put a new eVinci in, which is not a short duration type thing in terms of letting it cool down and shipping it off site to rebuild, but the swap over is pretty quick. We want to make sure we don't need to come down and do any maintenance during the operation fuel cycle on the reactor itself. We want to minimize our maintenance on the BOP systems for obvious reasons because of the power production availability. And we're generally using a factory build process. You know, it's not like a commercial nuclear power plant where you're going in and building up the site and bringing in a component and welding pipe and building buildings. This is more of a turnkey type operation with whole modules delivered to site and connected at the site. So having a low maintenance cost, maximizing what you can do at the factory in between refueling cycles has a lot of advantages for our customers. And so there is a strong alignment with those things and space, since we need to have high reliability over very long term with pretty much no maintenance. So with those challenges, you know, we have a pretty robust reliability program that we're developing. We do a look at it in terms of what are all our product requirements, all the way down to filtering that down, and how does reliability fit into that? What type of reliability do we need to design in at the component level, all the way up to how does that impact the reliability of the facility? And we're looking at using, obviously, inputs that you've heard discussed in the prior days over FMEA's requirement management and other things. But the goal of these graphics is to show you we're not just looking at what is the reliability of component XYZ. It's the integrated look of how that affects our PRA, which we have to use for a license, and also how does that affect our customer in terms of showing them that we are going to provide a highly reliable product. And a lot of these arrows that are only shown as one way are really a two-way arrows, and you'll see it a little bit on the next screen. But our reliability program has tentacles into just about everything in eVinci, because it's going to inform our ISI program. It's going to inform our maintenance program, any digital use of digital twins and how we develop digital twins. So it's got its tentacles in everything, and therefore we're developing it as a really robust program. This is the generalized process for reliability. It's really high level. Our actual process is much more detailed, but it's kind of like a next step. And it once again shows the iterative way that we're looking at things in terms of how are we going to do the work? How are we going to prioritize it? This isn't just like 5, 10, 20, 50 components. And we're not just looking at electrical components, I&C components. We're looking at the entire plant. How do we prioritize that work for thousands of parts, tens of systems? How do we broach areas where you have established availability and reliability analysis methods for like I&C components that everybody knows about, everybody can do? But for areas where we don't, more for mechanical reliability, for parts where they're not just active, but they're more passive components, heat pipes or other interfaces that are highly critical parts. How do you go beyond just defining your testing and general analysis and move that into the space of what you actually need to do to get more information to support reliability? So there's a lot of prioritization that we have to go through when trying to figure out how much we need to do, when we need to do it, and on what we do it. And then this is an overview of our tiered approach to reliability, kind of with the gotcha of, the more you do, the more it costs, the more it takes and schedule, the more and complexity it is. So are we going to be able to use existing data from suppliers or apply realistic derating factors to that data to make it applicable? Are we able to work with suppliers to get more data for new parts that they're developing based off of permutations of existing parts? Are we able to look at industry available data that's available in other sectors that aren't available from nuclear applications, and try to find ways to apply that data conservatively to get it? Are we able to develop empirical models or utilize existing empirical models? There are empirical models out there. How much those foundations have, especially for mechanical components, it varies compared to what we're used to in terms of our analysis. We have very stringent analysis requirements just from the typical deterministic analysis, which we often do physics of failure analyses, but we don't do them parametrically for reliability purposes. So determining what are the right empirical models that we can use that fit our failure modes and effects profiles, determining what physics of failure analysis we need to do to develop reliability data, how to maybe feed those back into development of new empirical models. And then for the stopgap, what actual testing do we need to do beyond the testing we're already going to do? We're going to test the heck out of an eVinci. What testing do we need to do beyond what we're already going to do just solely to satisfy our needs of developing reliability data for some of the components and systems? We do recognize that we don't need to do reliability analysis for everything. There are some things that we are able to screen out through various methods, but there's some things that we aren't. And once again, the biggest challenge that we have, and that we are really working to define the success path in terms of the amount of time and manpower and ability to leverage our experience and the industry's reliability experience and merge those, is in the mechanical regime. Electrical I&C. Oh, thank you. Electrical is, like I said, a little bit more of the industry standard and how you do it. You can go into ANSYS and do reliability calculations on circuit boards. You can get data off of many established databases, but mechanical reliability for non-active components, that's where it's a little bit more challenging in terms of figuring out what the right data is and what methods you should use to get that data to put in analysis. And this is my last slide. Thank you very much.
Great, thank you very much, Mark. Let me open up these questions. I have some questions for you, but I might add for the sake of time, I might put them into the chat if that's okay by you. But thank you very much for the interesting talk. We'll try to get back at 1 minute here. Nick, or I guess now we're on time. Next up, we have Nick Ralston. You're on there. If you want to, please share your screen.
Hey there.
Perfect.
Let me start my slideshow here. All right. Am I sharing the right screen?
Yep, you're all good.
Okay, perfect. Thank you so much. Well, I appreciate it. Yeah, my name is Nick. I'm an assistant professor at ASU. And I'm here to talk a little bit about a nascent PV technology called metal halide perovskites that we're currently studying and working on. I'm showing here a image of a canoe vehicle, which is one of NASA's recently chartered solar-powered vehicles that will be sent to the moon in one of the upcoming Artemis missions. And so I'm hoping that the types of materials we're using, these perovskites, could be leveraged for powering vehicles such as this one. Just to kind of frame the challenge here. Perovskites are, I'll talk a little bit more about them, but there's going to be, just in low Earth orbit, where you're talking negative 100 to 100 C, there are large film stresses that will develop because of the perovskites having these large thermal expansion coefficients relative to the substrates that they're normally deposited on top of. So that's one of the challenges. And of course, to survive lunar night, we're talking, almost negative 200 Celsius. So this is one of the considerations to have in the back of our minds that we'll discuss more about. But first, the promise and the opportunity. When compared to other, at least terrestrial technologies, perovskites have really done remarkably well in terms of their, this is showing AM 1.5 G spec efficiencies above up to 26% now, and AM0 is exceeding about 23.5% or so as single junctions. The amazing part about perovskites is that they can be tuned fully. This describes a crystal structure, so you can tune the band gaps and create tandems out of multi-junctions out of perovskites by changing the composition of the lattice. Additionally, one of the other benefits is that they are very easy to process in conditions that involve taking powders dissolved into inks and then cast through solution processing methods such as spray coating or slot die coating or blade coating. And so it's a technology that is extremely low cost, the lowest cost of any PV technology. Of course, when we think about extraterrestrial applications, we're thinking about generally 3-5 multi-junction. One benefit of these perovskites, since they're thin films and they're very tunable in terms of their processing, is that this chart here is showing the fact that they have the potential, when integrated into tandems or multi-junctions, to reach above 30% AM0 efficiencies and to have the highest specific power of any PV technology compared to the conventional 3-5 gallium arsenide based multi-junction cells. The efficiencies are likely not going to be quite as high, but they can be fairly comparable. And again, the benefit in having a order of magnitude improvement in the power to weight. And additionally, since these often contain lead in the structure, it's a very proton radiation hard material. So this is showing another study which observed the fact that these could actually withstand higher proton radiation fluxes than 3.5. So there's a lot of potential there in terms of space operation. However, some of the major challenges I mentioned about these stresses that can develop due to thermal expansion, and that can lead to delamination, and also under environmental conditions such as humidity and high heat, there can also be degradation. Now, fortunately, in space, we won't have to worry about humidity, but heat still becomes a factor. And so when we talked about we can talk about a driving force for delamination that scales as the square of the film stress. And when that exceeds the material's resistance to fracture, the fracture energy, then you have these damage processes that occur. So this plot here is showing the fracture energy, the material's inherent toughness versus stability on a log plot. Be up in the upper left-hand corner. That's where conventional technologies are, such as the 3.5s or silicon, which can handle. Now, silicon can't handle as much in terms of radiation, but at least in terms of heat, humidity, light, and such, and the combinations thereof, it does very well, and it's quite mechanically robust with these strong covalent bonds. Organic PV was a technology that was explored briefly, but didn't make it to market. Largely in part due to mechanical and chemical instabilities, and the real challenge with perovskites is they actually are the lowest in terms of the most fragile of any PV technology, and also the most unstable. So we're very much studying and trying to understand failure mechanisms in these perovskites and ways to improve on their lifetime. So here on are two examples of delamination occurring from long-term illumination and also from bending cycles in these structures. Basically, anytime you have environmental stresses such as radiation or sunlight or thermal cycling, that induces these stresses, these film stresses that can lead to delamination. And of course, then you have effects of efficiency reduction, of increased ion motion, and loss of ohmic contact, and ultimately device failure. So we've been working to engineer more robust perovskites mechanically through various techniques, and we've also been studying how these can perform at different temperatures. So we've started by looking at a combination of simulation and experimental work to understand how these voltage outputs and device performance would vary as a function of temperature. This is showing actually that performance tends to increase at lower temperature due to lower dark currents and less recombination. Now this is just going down, to about just about or just around -100 Celsius. But this trend is something we have to explore, is that even lower temperatures, towards lunar night temperatures, how these hold up. But we were able to confirm that with a certain configuration of our devices using silver electrodes, that we can match the same type of behavior as our model, and that we have low mobile ion concentrations. You don't want to have ions moving around in a PV device. That's actually
Nick, 2 minutes.
Thanks, Joe. And so this is one aspect. So we're able to design these devices that can handle at least low Earth orbit fairly well in terms of the temperature robustness. Now, the other question becomes, what happens over long periods of time? I mentioned about how these film stresses can lead to degradation, and during even just cycling from low Earth orbit, we can talk about changes of 200 megapascals or greater. And so thinking back to that formula, that we're going to have degradation scaling with the square of this tensile film stress, and so we want to minimize that, and we've actually been able to engineer devices that have compressive stresses. And so what's being shown here are devices that were cycled between -40 C and 85 Celsius. And basically, when you see film, both the red there is indicating a film that initially had tension, and after 200 thermal cycles, it turned yellow, and that means it's no longer a photovoltaic device. And through engineering in compression, through processing, and we add these polymer additives, we can actually create compression initially, and then they withstand these thermal cycles very effectively, and it retains its dark structure and remains operational after 200 cycles. And so we're just at the beginning of wanting to explore this in more detail and study kind of the interaction between space conditions such as these temperature cycles, but also things like radiation and then effects on them ultimately on the mechanical properties, so that we can design a robust and reliable system. And again, going back to the fact that any sort of environmental factor will lead to a mechanical driving force through stresses that then lead to degradation and fracture if we don't have robust materials. And so that's something that we're actively working on. And we're trying to design these systems for reliability. So with that, I just want to say thank you very much to the team, to everyone that made this happen, and happy to answer any questions you have via email or in the chat. So thank you.
Thank you very much, Nick. Very interesting. Lots of cool work going on over there at ASU. And yes, please make sure to post your questions into the Q&A feature here. And Nick said he will get back to you. So our next presenter will be Guillaume Pelletier. Hopefully I pronounced that correctly, from Dot Vision. Guillaume, are you on here?
I'm here.
Perfect.
Just let me set up the screen. I guess it's okay. Can you see my screen?
I can see your screen, yes.
Okay, that's great. So hello everyone, and thank you to invite me today. I will make a short presentation about smart submetering and the way it can enhance the future lunar power grid. I want first to take a little moment to introduce myself. So I'm Guillaume Pelletier, I'm the CEO of Dot Vision. Dot Vision headquarters is based in Paris, France. Personally, I'm graduate from Central Supélec Paris with several masters from offshore and spatial engineering, geophysics, and computer science. I worked for more than 20 years now in the field of energy management system, with a very strong focus from 10 years in industrial IoT, focusing on hardware and embedded AI, which is a very, very cool stuff to work on. So you have certainly understand yet that American language is not my native language. So I apologize if my pronunciation is not so good, and I will help myself sometime reading the slide instead of explain what is on it. So the agenda, we're gonna make it very fast on the current challenge in the lunar power grid. We're gonna introduce what is the smart submetering technology, and based on Earth's current application, and we conclude fast on the subject. So on introduction, we all up to date in the fact the lunar environment is particularly harsh. We all agree on that. So I'm going to talk here about technology implemented on Earth, actually, and that could optimize the management of the lunar grid. One of the solutions that could optimize the management is a real-time smart submetering technology. So by incorporating the underlying concept directly at the design level, we will be able to create a system that will not only be dependable, but also safe for the people who are working on the moon. The current challenge we face when wanted to deploy lunar power grid, the first one is has never been done. And we have to take experiences from the Earth power grid, and we see that the Earth power grid has been predicted to encounter several difficulties that will affect dependability and effectiveness. So the lunar power grid will be built upon new concepts, and we will try to eliminate historical infrastructure and constraint. As I told you, the significant challenge is environment. We can arm equipment and enter power transmission. So this challenge is to provide power to remote and isolated location and mobile location. It needs to be planned carefully. So let's go quickly on what is submetering. So if we take a broad definition, submetering is a practice of measuring the usage of specific component into a bigger component or a complex component. This is usually done by installing meters beyond the main unit meters to track consumption, production of individual device, unit of section of the complex container. We can make the parallel with your own home. Imagine you were able to know in real time the consumption of any device, from the light bubble to the heater, in real time at your home. The underlying process is then called disaggregation, because you have with the main unit you have the whole consumption, and the disaggregation give you the information in real time of the consumption of any device. Also, we can introduce what we call smart submetering, which involve integrating artificial intelligence, which is AI functionality. And why we need to introduce an artificial intelligence on the side of the smart metering, because the smart metering, as you can imagine, just gather and produce a lot of data, and everything is what we will doing with this data. Measuring is okay, but measuring, if we don't do anything with the data, it's a nonsense. So smart submetering will help us to use this data in a intelligent manner. So what are, based on the experiences we had on Earth, again, we deploy since 20 years a lot of smart submetering system. The core components are a real-time sensing system. I mean, the sensor who can measure in real time electrical or any flow. A real-time telemetry and time series. I mean, we gather and now we have to send the data. We have to also rely on real-time eventing, which encompass the alarm and the way we treat the alarm. And finally, the real-time analyzing, which is the part what we are doing with the data. Based on our experience, again, we have found that the RT operating system is the only essential component for submetering. I mean, the hardware samples serve as its support. This is very important because several companies try to sell product and hardware products. This is not the key point. The key point is the firmware. And when we speak about the firmware, we speak about a real-time operating system with all the protocol and stack and driver which are enable seamless communication, seamless sensing, and intelligent processing of the data. When we speak about intelligent processes of the data, we speak about distributed AI, and we can introduce maintenance, which is very interesting to mitigate the difficulty we can encounter on a harsh environment. So distributed AI and predictive maintenance are really two cutting-edge technology because this is brand new. It's only present in the industry since only a few years, but this may enhancing the way we manage the future lunar power grid. The first, the distributed AI, then we can create a network of intelligent sensor. That's very important because centralized intelligence, it's not so good in terms of reliability of system when we have this kind of environment. And at device level, we can use the intelligence
Hey, Guillaume, 2 minutes.
2 minutes, okay, to predict failure and doing what we call today predictive maintenance. This is very interesting. So the feature that's enabled with this kind of technology is efficiency and health. I don't let go through because 2 minutes will be enough. In order to gather all the information and be able to react in real time, we also need a command center and control capability. This is what we've done for several utility in Europe and also for some industrial. Based on this, again, I done my introduction and told that everything is based on a huge experience on system deployment on Earth. We have deployed system on industry, in aerospace industry, and some factory, a lot of factory indeed, use our system to monitoring machinery and reduce the footprint of CO2 and the cost of the operation. We also have a very interesting scenario in the highway industry, also in the building and cities. The device we're talking about, this is one you have on the screen now. It's very small smart meter that you can put almost anywhere. The packaging here is to be standard with the electrical system, but it's very small and you can fit it in any component. In conclusion, we have very briefly explained what submetering technology is and how it has to be implementing in the future linear power grid, because is something we experience very useful on Earth project to take action. So we are prepared to offer to the partner or the audience some meter unit to enable them to begin to test and to use this kind of system and interconnect other subsystems. We began also on our side to testing and modify our electronic in order to support space deployment. And we are exploring IE management, but this is more area stuff because we go very deep inside the algorithm and new technology. So thank you very much.
Thank you very much. This is very interesting, and I think you'll probably be getting a number of questions through the chat feature. So
mainly because I have some difficulties to explain. Sorry for my English. I don't speak oftentimes since, but hope it was clear. And again, thank you very much for giving me the opportunity to present.
No, very clear. And I'm referring to your implementation of AI management into extending reliability. So you might get a question from me nonetheless. So
Yeah,
thank you so much.
You're welcome.
So moving along to our next talk, we'll have Nadeem Mahadik presenting.
Hi, yeah, I'm here.
Perfect. Are you able? There we go.
Can you see my slides?
Can see your slides. Fantastic.
In slideshow. All right. Is it in slideshow mode?
Yep, and it's on the right screen, and I'll tell you at the 8-minute, or give you a warning at the 8-minute mark.
All right, thank you. So yeah, thanks everybody. I'm Nadeem Mahadik from Naval Research Laboratory, and today we're just talking about some reliability studies, more fundamental studies on silicon carbide materials and devices for extreme environments and harsh environments as well. We have been doing this silicon carbide work for more than a decade now, actually quite longer than that, but more it was, we have successfully made it commercial. It's, you can buy parts right now that are for terrestrial applications, but we still need to do some more work so that it can go into space. But there was one defect in particular that I would like to talk about. That was the secular defect, and that is called known as the basal plane defect. And This is actually a line defect that has been big issue, and people have dedicated a lot of effort to resolve this. So the defect is basically upon carrier injection, when you inject electrons and holes, just by current or however, it causes the forward voltage drop. Yeah, it causes the forward voltage to drop, and then the device fails. Also, in off-state leakage, it increases your leakage. But since many we have done a lot of work, and over 99% of these BPDs, so-called, have been successfully converted to benign cutting-edge specifications. So they are not an issue as such. But now there are other sources and other issues. So one of the key things that was utilized to see these, how do we see these defects is an NRL invention that is a wafer mapping using ultraviolet luminescence, where we can get like a 1 micron resolution, and we can measure up to 200 millimeter diameter wafers. So this has been the key to solving this problem, investigation solving it. Also at NRL, we have a capability which is like a synchrotron style X-ray topography, but it is in a lab scale model, where we have a very high powered source, and we can map again 200 millimeter wafers. We can do all kinds of different geometries, and we see the extended defects in all these different kinds of geometries. So just very quickly, this is a survey of more than 100 wafers. This is the state of the art wafers. We just did it over the last couple of years. And we have wafers, and as you know, silicon carbide is the only mature technology which has devices available up to 15 kilovolt range in the market. So we have done a study on these from a 10 kilo 1 kilovolt all the way to 20 kilovolt, and we see a large variation. We have automatic defect counting mechanisms here, and we see that for the low voltage class, there are it's very reliable, but as soon as you go to higher voltage class, the reliability tanks significantly. So, and this is about 6 kilovolt devices, the reliability tanks a lot. So we are trying to figure it out. Also in this 3 kilovolt range, this is actually a very important voltage class, because you can make them and then derate them however you want to get high voltage applications. So we focused on this devices more. So I'm going to show you like 3-hour talks in just 10 minutes. So please bear with me. So first, I would like to talk about robustness of 3.3 kV MOSFETs that were made, and we have very high carrier injection operation, extreme level of carrier injection. So this is a typical D MOSFETs, and we fabricated with the collaboration with industry, 12 wafers that had thousands of MOSFET devices like this, and we had different splits. We had room temperature versus high temperature implantation, and then we stressed hundreds of die using different power levels, and we inject the carriers using the UV illumination. And this is simulation of a current, like a high injection current, like a pulse. So it's similar to like lightning strike, 10,000 amps per centimeter square, for example. And then we observe. So when we do it at low current densities or low carrier densities, both the room temperature as well as the high temperature, we do not see any defects, when we image them. But after we increase our carrier density, and in here we are basically having a carrier density of around 1 times 10 power 18 in the P plus contact layer, we see that the room temperature, from the termination region, we start to see these defects, and that will be a big reliability concern. So at normal typical operation, it does not fail. But when you do a high temperature operation, they will, when you do a high injection condition, then these room temperature implanted samples start to fail, but they only fail in the termination region. So we wanted to look at it more carefully, and we see that we take one of these devices and then we even go higher. This is the full die, and we go as high as 13,000 plus watts per centimeter, which is equivalent to 10,000 amps per centimeter square. And we have several defects that are generated from the termination region, but the good news is that the active region, it shows no stacking fault expansion, as I show you here, and it's all the active region. And the active region is the region that sees your high current injection, so which demonstrates that the silicon carbide MOSFET, the 3.3 kV, is robust for pulsed operation, or it is immune to lightning strikes or any other things. So why is it causing these stacking faults to come in the termination region? So we did some TCAD modeling, and we see that when you have this P plus contact on top of this P well in the active region, this is an active region, the P well buffers the carrier injection, and this simulation has been done at around 10,000 amps per centimeter square injection, and you never reach, the minority carriers never reach the level of background or higher than that. So it is that you do not have so much recombination at the basal plane dislocation, causing it not to fall. So this technique actually can now be used to make the termination also robust, wherein you can just have a double implanted layer. So that is one of the
2 minutes.
Yes. Okay. So the next two I'm going to quickly go over is some NASA samples. It's a JFET samples. We did analysis, and I'm going to show you two defects. And they're making JFETs because the reliability of JFETs at high temperature operation is much better. So here I can show you this is a device, and we see these defects. We did topography, and from that topography we see these defects, interesting defects right under the device. In the UVPL we see this dot-like contrast, but we have a technique called depth resolved non-destructive investigation, where we see that this is the side view from the cross-sectional view, and we see that this defect actually goes throughout the substrate. And we want to, now we're still waiting to see what is the impact of that on devices. Next is, we see this another defect. It looks like strain bands that go across, and these strain bands have a highly localized lattice distortion and bending of the bands, and that will definitely have an impact on some of these devices. So we want to see now correlated how we are waiting on some electrical data to see how they're going to impact. Next, I'm just going to show you a quick thing about what we are about to start next. And this is we are trying to develop a semi-superjunction silicon carbide power transistor, which will have much higher radiation tolerance as well as low on-state resistance. And the reason is because we have this unique recombination enhanced layer on the bottom to improve the radiation tolerance, as well as we are developing this novel channeling implantation, as I show here. So you need, implantation is typically done so that the lattice actually gets damaged. But what we are trying to do over here, we have, the aluminum ions. We just find the channel, and finding the channel, we developed a method using multi-azimuthal X-ray rocking curve measurement. We find the channel, and then we do the low damage, channeling implantation. And we did this, and we see that the rocking curve width, which is indicative of damage, it does not change before and after implantation. So this is a key enabler for channeling implantation. So using this technique, we recently saw that It also goes much deeper, so it's 2.5 times deeper.
Nadeem, if you can wrap it up, please.
Yeah. So aluminum can be implanted very deep using this one. And the last slide I have is showing that we have another capability of a pulse laser single event effects NRL facility, where we can simulate the single event effects on our devices, which we will be doing, and on our devices to see what is the LETs that can be that can be our device can withstand. With that, I'd like to thank you and take any questions in the chat.
Thank you very much. Yeah, it's great to have some world-renowned device physicists right down the road trying to improve our device capabilities so that the reliability overall of our systems will be that much better. So if you have any questions, please or if anyone has any questions, please feel free to include them in the chat, and Nadeem will get to you as quickly as he can, I'm sure.
Thank you very much.
Thank you. Next up, we have Olivia Formoso from NASA Ames Research Center. Hi, Olivia, I can see you here.
Great. Can you see my screen?
We can see your screen. If you want to hit the...
Okay, great.
Great, thank you.
All right. Hi, everyone. My name is Olivia Formoso, and I will be talking today about robotic assembly and reconfiguration of modular power management and distribution systems. This work was conducted at the Coded Structures Laboratory within the Intelligent Systems Division at NASA Ames Research Center. So to enable sustainable exploration in space, power systems must be lightweight, efficient, and be able to operate in harsh environments. Modular power management and distribution systems have the advantage of reusability for other missions, adaptability to changing environments, and ease of integration with other systems. And given communication delays and blackouts in lunar regions, these systems must be built and maintained autonomously. We know that crew time is precious, and therefore robotic assembly of these systems is critical. So we've been thinking, how do we leverage autonomy and robotics to build lunar power systems and infrastructure, and how do we do this in a sustainable manner? These are questions that the Automated Reconfigurable Mission Adaptive Assembly System, or ARMADAS project, is addressing. ARMADAS consists of a fleet of mobile robots that autonomously deploy and assemble structural units to support a variety of different missions. So here in this picture, you can see the ARMADAS robots are building a habitat structure first, and then disassembling that to build an antenna. ARMADAS is a building block assembly system that integrates discrete lattice building blocks with high mechanical performance, task-specific relative robots, and algorithms enabled by this discrete environment. And these three components give us a scalable, robust, and autonomous assembly system. And I'll go over these three sections in detail. So starting with the material system, the lattice structure is built using discrete unit cells, which we call voxels or volumetric pixels. They can be reversibly assembled to create larger structures. These lattice structures have the advantage of being an ultralight system while still maintaining high mechanical performance. So instead of one monolithic structure, we can take a bunch of these unit cells and assemble them together on site like Tinker Toys or Lego bricks. And on the left, we were able to show that these structures are reconfigurable and have a high packing efficiency. You can see that our teammates went out to Yosemite and built a bridge, a shelter, and a boat using components that were packed into 2 backpacks. They are scalable and tunable, and you can easily assemble thousands of these voxels. And by mixing and matches the different types of voxels, you can precisely tune the structure's mechanical behavior. So in the picture in the middle, we use 2 different types of voxels, one that is more compliant and one that is more stiff, to tune the aeroelastic response of the wing structure. And they're also ultralight and repairable. So you can load these structures until failure, replace that one broken part, and then reload that structure, and you'll keep your mechanical performance. So we've made these discrete metamaterials using different forming processing, different materials at different scales and with different geometries. And we think that this building block approach can be a powerful one for lunar and in-space assembly. So now that we have this high-performing structure that we can tailor to mission-specific applications, how do we build these structures and how do we assemble them? So due to the structures, So due to the structure's discrete repeating nature, they are well suited for large-scale robotic assembly. And we've been focusing on a class of robots that we call relative robots because they operate exclusively on the structure. They leverage the periodic environment for their indexing metrology and error correction. So this allows the robot to build something that is both larger and more precise in itself. Because the lattice provides such a well-structured environment, the robots we develop are relatively simple and very small compared to the structures that are being built. So in this bottom video, we see an early prototype of an interim robot that is locomoting on the structure. And this robot doesn't have any sensing. It is completely open loop. But its 100th step is just as successful as its first, and its accuracy and precision is that of the overall structure. On the right, we have an internal crawling robot that is able to locomote between adjacent faces and bolt voxels together at their faces. So these robots are co-designed with the unit cell geometry and can locomote externally or internally throughout the structure. And we envision a range of robots that will perform assembly tasks, system of health checks, and outfitting of the structure. The discrete environment is important for algorithmic benefits and scalable autonomy. So here the videos on the left show a single robot building many different structures. And on the right, by adding multiple robots working in parallel, the system has the ability to scale to much larger structures and increase build efficiency. And we can use typical multi-vehicle and multi-depot routing algorithms for robot motion planning and assembly. So how can we outfit the structure to specific applications? Our latest demonstrations consisted of all basic structural voxels, but we are working towards voxel outfitting capabilities for a wide variety of applications. So here we have a proposed lunar construction kit with various unit cell types. For example, we have the basic structural voxel, a rail voxel for transport, structural panels for walls, integrated solar panels, voxels with integrated electronics to allow for power and communication routing through the substructure, and a footing voxel that is able to interface to the variable terrain. So we can choose specific voxel types and integrate them together, such as the robot charging station on the left that uses the solar panel and power voxels. If we add in the rail and basic structural unit cells, we can create a powered rail system shown in the middle. And this elevated lunar rail setup could provide some dust mitigation strategies during transport of materials and equipment. On the right is a tall tower for communication between different sites. And here we have the adaptive feet of the footer voxels that would require minimal surface preparation for the build. So to demonstrate a potential modular solar panel for robotic assembly, we built a simple first prototype of a solar panel voxel. So this is a panel with 4 solar cells that are mounted onto this basic structural voxel. The panel has electrical contacts for power and ground on all 4 sides. And this allows us to have an orientation independent panel for ease of path planning and robotic assembly. These passive connections were used just for the ease of this first prototype, but we envision that future versions of this panel would have electrical connections that are actually robotically actuated to connect the wiring. So as the solar panel voxel is attached to the existing structure at the build front, the solar panel module forms a passively coupled electrical connection to its neighboring solar panel modules. So we performed a small-scale demonstration of robotic assembly of the solar array. The robots placed 10 solar panels in the array, and each time a voxel was attached, a green light would illuminate on our bus voxel, which you can see at the bottom left of the array. We also had current monitoring on the system and observed a current jump as a new panel was attached to the array, ensuring electrical connection was successful.
2 minutes is your warning.
So here's a video of our one panel being added. And as you can see, when the panel is aligned and placed next to the neighboring panels, an electrical connection is made and the light on the bus voxel turns green. And there is a current jump on the TV screen. So the voxel is placed by the larger robot, as you can see here in the video. And there is a smaller internal robot that is performing the bolting of that newly placed voxel to the existing structure. It's a little bit hard to see because it's blocked by the panels in this video. We also showed a first demonstration of robotic cable routing throughout the structure. Here, there's a bus voxel on the bottom left, shown with a lightning bolt, and the internal robot attaches the cable to the bus voxel using a snap-fit connector. It routes the cable to a payload on the top right side of the structure. And it's hard to see in the video, but as the robot traverses through the structure, the cable harness is being passively released as the robot locomotes through. The robot connects the other side of the cable to the harness to the payload on the other side of the through a snap-fit connector. And the Armada sign lights up, demonstrating successful electrical connections and cable routing by the robot. So here is a proposed ConOps for Armada's autonomously building a power system on the lunar surface. All components, including the robots and the voxels, are housed at a base station. And so we have autonomous assembly by the robots and algorithms, and the robots are attaching both structural modules, which are shown in black, and the solar panel modules shown in blue. Once the build is complete, the robots can perform cable routing from the solar panel array to a payload or power system. And over time, the system can adapt to changing mission requirements or environmental factors. So if the mission objectives change or modifying the shape of the array avoids shaded areas over time, the robots can then reconfigure the solar panel modules into a different configuration. And we can add more payloads as needed. Also, if one panel gets broken, the solar panel module can be easily and autonomously replaced with minimal downtime of the system. So the key utilization of the Armada project is the adaptability and reconfigurability of its base components. The multifunctional unit cells, integrated task-specific lattice robots, and potential for high autonomous control will lead to long-term mission cost savings and reusability of components that can support a variety of different missions over their lifetime. And this system of modular panels, along with autonomous assembly and maintenance systems, can enable higher mission adaptivity and increase power system life cycles. And this is our current team, and I'd just like to highlight the PI of the Armada's project, Kenny Chung, Christine Gregg, our chief engineer, and Peter Zell, our project manager. And yeah, that's it. Thank you for your time, and I'm happy to answer any questions.
Thank you so much, Olivia. There's already a question for you in the chat or in the Q&A area, so you can look right at that. Very interesting talk. Thank you so much. Curious to see how those little things will do out there in space building stuff. I could use some at home. So next up, keeping us going forward, our last presentation for this section. Already perfect, Patrick. Thank you so much for joining us and getting all set. So yes, exactly. You're from Xeno Power Systems, and you'll be ready to start whenever you're ready.
I had to find you on mute. Thanks, everybody. Happy to be here. Thanks for having me. My name is Patrick Snoffer. I'm the Senior Program Manager for Field Supply Chain at Xeno Power Systems. You heard from my colleague just a little bit ago, Jacqueline, kind of about a little bit high level of our company. I'm going to go a little bit more in detail about our technology and kind of how we anticipate to scale it and really help the commercial space industry address some of the power needs that we've been talking about here. So kind of RPSs have been utilized in space for years. They've successfully been there. They've shown that they're capable of reliable long-term power. But if you look at the current state right now, even NASA's marquee missions does not have, you can't meet their power requirements with RPSs alone. So you can see there's some there, and while some of the missions may benefit from an RPS technology, they're not able to supply them because they're currently commercially done or done by the government through DOE with the plutonium-238 systems. So we are really looking to make this a broader technology and available to commercial and not just governmental actors for it. So kind of historically, what RTGs have looked like. We have on the left here a plutonium-238 based system, SNAP-27, that was deployed on the moon, very high specific power, very reliable, and this is what we have flown a lot of plutonium-238 RTGs over the years. On the right is a strontium-90 system, very low specific power in this case, and this was a terrestrial deployment of strontium-90 RTGs. We have deployed the U.S. has deployed over 100 strontium-90 RTGs. Worldwide, there's been over 1,000 strontium-90 RTGs. But really, the reason that they've been based for terrestrial systems is because they are, it takes a lot of shielding requirements for them. And part of that is, even though strontium releases a beta, which is relatively easy to shield, you get a lot of Bremsstrahlung long radiation through the shielding material and it releasing photons, and it ends up being shielded more like a gamma radiation. So you end up getting really heavy systems with low specific power. So this is where Xeno comes in. We evaluated the technology and looked at all the history of strontium-90 RTGs. We have come up with our own fuel matrix and shielding design that actually reduces the shielding requirements for strontium-90 RTGs by an order of magnitude and greatly increases the power density. So this is what we're excited about. This is what will enable strontium-90 RTGs to be deployed in space. And this is what we are using, as we mentioned, with the defense contract for a satellite deployment. And really, we built our technology around an isotope that was well known, had a lot of history with strontium-90 RTGs, and then also a supply chain that we can use today, and then also scale it up for the decade to come to meet the actual commercial demand outside of what's just being done by the government. So as was previously mentioned, we're really going to start fabricating our systems next year with a completion date in 25 and a target launch date in 26 for our systems, which would be the first strontium-90 system launched into space. So when we're kind of looking at it, what can we do and what are we providing? We're all here to provide reliable power on the lunar surface. We all kind of know about that, but what Xeno's really looking at is really to be able to kind of go through the survive and operate the lunar night with the reliable RPS power. So we have three kind of different technologies that we're developing. The typical RU, just heat, roughly 50 watts thermal. This is the easiest technology to deploy, very simple, and we can do things like enable communications and PNT on the lunar surface. So as you have lots of different sensors around that are going to be developed for various different things, if they need heat source, a RU is a great application for that. RTGs, if we're looking at electrical power here, on the order of 10 watts electric is kind of what we're initially starting, and we're going to build that up. And you can add them in module form up to probably what we see is about 500 watts electric. Thermoelectrics have a very proven reliability in space, well known, and we just want to bring that to the commercial market as well. And then as was kind of the RSGs, the radioisotope Stirling generators, you get a higher efficiency from the 5 to 10% efficiency of thermoelectrics to above 20% for Stirling generators. And we're really looking to help work with other technology partners to deploy these in space to do the RSGs. And here we're looking at tens of watt electric to up to a kilowatt electric, again, depending on modularity and scalability there. So that was kind of our technology, but how do you meet large power requirements and things that are going to be required for the lunar surface? And so the good thing about strontium-90, and one of the reasons that we were selected, is it's widely available in used nuclear fuel. It is a fission product that's roughly is formed in roughly 6% of fissions that happen in nuclear power plants. So there's a lot of it sitting around in using nuclear fuel. Currently, other countries such as France and Japan reprocess their fuel, and they've been doing it for decades. It's a very well understood technology. And then previously, the Department of Energy in the US used to separate strontium-90, and this was done in the 60s and following decades. And we actually produced our own strontium-90 to deploy the terrestrial strontium-90 RTGs in the US. So that technology is very well understood as well. And if you look across all the used nuclear fuel in the US, there's over 10 megawatts of strontium-90 that would be accessible. And between international parties and there's strong domestic companies that are looking to commercialize reprocessing in the US, there'd be a lot of availability of strontium-90 from the used nuclear fuel. And one of the benefits of using strontium-90 is right now the power industry considers it their waste. So if we have a way to utilize that, beneficially reutilize that for power, especially in space applications, we can make both reprocessing more economical and fuel, the strontium-90 fuel itself, economical. And so we are partnering right now to unlock a large supply of strontium-90 by the end of the decade. This would be roughly equivalent of 120 GPHSs. So we're talking tens of kilowatts available of strontium-90 per year is what we'd be able to unlock there. So
2-minute warning.
Okay, thank you. And so on the right, the graphic is just fission process that shows strontium-90. And so really, in conclusion, what we're kind of saying is that we know there's an abundant need for affordable, dependable power in space in all applications. Our technology complements what NASA and DOE is doing for their RPSs with the plutonium-238, but this would actually provide it at scale to everybody else who has a demand for power in space. And we are working to deploy these in the near-term future, but also to build a supply chain for a very large, robust commercial supply by the end of the decade. So we're both tackling it at the near term and then also getting ready to scale for long term. And we really want to be able to supply power for the needs here. I will say one other thing, the tipping point news was we were really excited about. Americium-241 is also found in used nuclear fuel and can also be coming off of reprocessing there. So there's access available to what is considered waste for both americium-241 and strontium-90. And we're excited to be able to start developing that RPS kind of system as well. So thank you, and happy to take any questions in the chats or over emails.
Thank you very much there, Patrick. And yes, congratulations again to you all at Zeno and on the recent announcement. So giving one last second for anyone to jot down your email and of course, ask any questions through the chat. Otherwise, I'm going to steal the screen here and thank everyone. Well, thank everyone first and foremost for their time and their talks. It was very interesting all around. Next up for us is actually a small break. So we will be back here at 2:15 to start the next sessions.